My name is Anna. I'm a software engineer, and I work for a company called ADA, where in addition to having great people and technologies, we also built a system that analyzes different medical images, detects pathologies in real time, and helps radiologists be faster and accurate. And I'm here to talk about a concept called object-oriented design. So, what is object-oriented design? Basically, it's a set of principles and techniques that can be used to build large systems that are modular and can be managed and scale and also change if needed. Now, this concept is a relatively new concept, well, at least in archaeological terms, because it's been around for more than 50 years. However, I don't think it makes it any less relevant today. I would even argue that concepts that survive past their height for so many years have something fundamentally right about them. And my main claim for this talk is that object-oriented design is a universal concept that can be used not only for application code, but also for infrastructure code. And we'll end with a short disclaimer that I'm not going to cover all the theory of object-oriented design, but instead focus on the essence of OD and show you some of the very basic and common techniques that you can use to build better systems. The concept of object-oriented design is often mentioned with some other big words like inheritance and polymorphism, and implies that you need to build some complex hierarchies and have multiple levels of abstractions. Now, I'm not saying that these concepts are unuseful or bad. I just claim that they are not mandatory to build awesome systems. Which brings me to what is OD and how it came to life. So, supposedly the person who coined the term is Alan Kay, computer scientist and one of the developers of Smalltalk, one of the first object-oriented languages. And what he tried to solve is to build systems that are composed of modular components that actually don't use shared state, but instead use messaging to communicate. This design leads to a system that is really modular. It can scale well. It can be broken down to microservices and even run on different machines, leading to a decentralized, a distributed system. That is most important property is that it's resilient to change. So to me, the essence of object-oriented design is mostly about change. And more specifically, build systems that are resilient and adaptive to change. And you will see this theme of change as a common theme through the many object-oriented principles. Because, to be honest, we as engineers have this tendency of trying to build the perfect software system. But I think that the main goal should be accepting the inevitability of change, and instead of building perfect systems, simply build systems that are more adaptive to change. So if that was the case, and it's all about change and building decentralized systems, then how come today object-oriented design is mostly associated with Java, C#, and other languages that will make most operations engineers run in terror? So to understand why, we need to take a short trip back in time. So how did we get here? If we go to around the 1960s, there was no real difference between infrastructure code or application code, and everything was basically the responsibility of the almighty computer programmer, who was doing the job of hardware engineer, software engineer, IT expert, and even an electrical engineer if needed. So if you think it's tough to find skilled engineers today, think again. So some time has passed, and software has developed in its own separate discipline, and cross-platform languages are different software containers and platforms did a very good job of abstracting the infrastructure from the developers. So software engineers started to build large software systems instead of just programming the machine. This, of course, created new challenges. And this is where new concepts and techniques like object-oriented design came to save the day and were widely adopted. Now, at the same time, infrastructure world also had its own exponential growth, And for many years, the focus was mostly around hardware and performance, databases, building networking infrastructure, and of course, small little things called internet and the cloud. And finally, where are we now? So some more time has passed, and infrastructure became more and more sophisticated and complex. It started requiring some more automation and other solutions from software to deal with these new complexities. And at the same time, software engineers also reached the end of their capacity of building scalable and large systems without paying more attention to the underlying infrastructure. So now, these two very different paradigms are closer than ever. And I think this is a really good opportunity to start borrowing concepts, the successful at least concepts from each other. And one of these concepts, at least in my opinion, is object-oriented design. So to start describing the principles of object-oriented design, let's first define what's our basic unit of work. And in object-oriented design, it's unsurprisingly an object. So what is an object? Basically, it's an independent entity that has an internal state, a set of operations that define how the object communicates with other objects, and hopefully it will have a very specific purpose. So let's look at an example. Now, what you see here is a very simple Docker Compose configuration. Now, Docker may be not the first thing that comes to mind when speaking about OD, but I think it's a very good example that demonstrates the concept of an object, because Docker container is an independent entity. It has an internal state. It even has a type in form of a Docker image. It defines clearly how it interacts with the outside world, and it has a very clear purpose. In this case, you have two objects. One is a DB service, and another one a simple admin service for the DB. Okay, so now let's go to, well, I'm going to cover only two object-oriented principles, because as I said, it's a short talk and we need to focus. So one is the single responsibility principle, and the other is dependency inversion. Both are part of the so-called solid principles, which are very common in object-oriented world. Now, single responsibility, or SRP, is probably the easiest concept to explain, but the hardest one to practice in reality. So the definition is that your object should only have one clear purpose, or as Robert Martin defined it, only one reason to change. Remember, change? So, what is SRP? So the idea here and the main goal is to keep us from building a monolith large system, and instead building small components that have very clear responsibility. And if I quote Robert Martin again, he defined the essence of SRP as you should gather together the things that change for the same reasons and separate those things that change for different reasons. Now I try to say it really fast 10 times. So the idea here is, again, to limit the impact of change, because if you accept the fact that your system is going to change, so when it happens, you will be very lucky if it will be limited to a single component instead being forced to change your whole system. And another side benefit is if you gather together similar functionality, it will also be easier for you to test this functionality. Let's take an example of how we can use this universal principle in a restaurant. So let's say we go to a small family restaurant. You will usually see what I call a one-man show. You will see the owner of the restaurant, who is also the waiter. He will take your coat, he will sit you at the table, and also bring you the food, which might be very nice and cozy and maybe even efficient for a small place. But if it gets bigger, what usually will happen is that you will start hiring more people, and more importantly, you will assign clear responsibilities to each person. You will have a hostess, you will have waiters, the cook, and probably someone that will wash your dishes. And this might be a bit less cozy, but it is much easier to manage, scale, and change if needed. So even if you want to test this principle for yourself, the next time you go to a nice restaurant, just try and make the hostess bring you some food, and you will see just how protective they are of the single responsibility principle there. Okay, this brings me to the next principle, which is called dependency inversion. The definition, again by Robert Martin, is that high-level modules should not depend on low-level modules. Both should depend on abstractions. Now, as your system starts getting larger, you by nature start building more complex objects. Now, this will quite naturally introduce more dependencies between the objects. And more dependency it means that your system is much less resilient to change, because one object affects the other. So instead, dependency inversion implies that you should use very simple objects and wire them using abstraction. This, in turn, will limit the impact of future change. And again, it's much easier to test because you can use mock dependencies in your test instead of actual dependencies, thanks to the abstraction. So if we go to the restaurant analogy again, we might want to provide a delivery service for our customers. Now, one option is to develop an in-house delivery service, which will give you a lot of control. You will define exactly what kind of a service you need to provide, but of course you will need to operate the whole thing, to hire the personnel, and hear the complaints of the unsatisfied customers. Another option is to outsource your delivery service, or as we call it in the software world, an abstraction. Now, you can use Vault or some other fancy delivery service, but in both cases, it will reduce the control you have over the service, but it will also reduce the dependency. And in the future, if you would like to change your delivery service, it will be much easier. So now let's go to some practical details. Now, I want to demonstrate these principles and how they help us to redesign our system in ADOC. So we work with hospitals, so we have two main services. One is the on-prem service that handles all the communication with the hospital, the data services, the identification, and a bunch of other stuff. And the other one is the backend service, which we call the analysis server. And its main objective is to analyze the medical data and provide insights or anomalies. So this was really basic architecture, but it served us quite well when we only had a few hospitals to serve. But the main pain was that we had to set up a new backend service for each new site, which was also very difficult to deploy. It was not scalable. It was really expensive. But fortunately, we had an exponential growth, and we had to re-architecture this thing to succeed. So this is really roughly our architecture right now. You don't need to understand every icon. The main idea is that we solved our main pain and created a more dynamic backend infrastructure. So by taking our backend service and breaking it down to smaller components, by extracting all the internal dependencies like configuration and communication to external components, by using console, queues, and external DB, etc. So now let's take an example of how we use the single responsibility principle. So probably the first step in object-oriented design is to identify your objects, to take your large system and break it down to components. In our case, it was we had several main components. One is our web API, the DB service, the configuration. So each of those got their own component and responsibilities. For example, the web service is now responsible only for the communication with the on-prem service. The configuration service, instead of being a component of the analysis, is now an external entity. And also abstracted all the DB service operations and delegated it to another service. Of course, all of these things were also reflected in our deployment process. If before we only had like a bunch of bash scripts that deployed everything, we now have a modular deployment process using Terraform and terragrunt. The second example is how we use the dependency inversion principle. So this is just one example of how we took an internal and local configuration, extracted it to console, and abstracted it from the analysis server using a configuration service. So in the future, if you want to change the implementation, the analysis servers will have very little impact on it. And finally, this is a very simple example that demonstrates how you can see dependency inversion in tools like terragrunt or Terraform. And this is the way we deploy. I hope you can see. Well, you probably don't see anything, but this is the way that we deploy our RDS cluster. And we use terragrunt, which is a thin wrapper on top of Terraform. And it makes it much easier to reuse different Terraform modules for different environments, and also make our deployment code much more object-oriented. So in this case, you can see that our RDS cluster has a dependency on our VPC, but it's a really, really abstract dependency. And if it doesn't really know anything about how it's implemented or who created it, and if we want to change it in the future, it will be much easier to change. So let's bring me to conclusion, some takeaways. So first, hopefully I made my point and show you that object-oriented design is not strictly the propriety of software engineers or application code. It can be used universally in infrastructure code and even in a restaurant. Second is that there is a bunch of information about object-oriented programming online, so I urge you to go and learn for yourself and find the principles that work for you in your system. And finally, when you start applying the principles, just keep it simple, because you don't need to get good at object-oriented design. This is not the goal. Remember that the real goal is to build systems that are good at being adaptive to change. Thank you.